तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the first lecture of Module 5 on Analysis and Design for Shear and Torsion. In this lecture, we shall study about the stresses in an uncracked beam first. Then we shall learn about the types of cracks generated in a reinforced concrete and prestressed concrete beam. Then we shall learn about the components of shear resistance, the modes of failure due to shear, and then we shall learn about the effect of prestressing force in a shear type of failure. The analysis of reinforced concrete and prestressed concrete members for shear is more difficult compared to the analysis for axial load or flexure. The analysis for axial load and flexure are based on the following principles of mechanics: equilibrium of internal and external forces, compatibility of strains in concrete and steel, constitutive relationships of materials. When we studied these two actions earlier, we based our equations on these three principles, and the behavior of the member under each of these action was well defined, and we were able to plot the complete load versus deformation behavior for a member under axial load or for a member under flexure. But for shear, this is relatively much more difficult. The conventional analysis for shear is based on equilibrium of forces by a simple equation. The compatibility of strains is not considered. The constitutive relationships relating stress and strain of the materials, concrete or steel, are not used. The strength of each material corresponds to the ultimate strength. The approach that we followed for axial load and flexure was more rational compared to the approach that we shall follow in shear. For shear, we shall consider only the equilibrium of forces. We are not considering the compatibility of strains in the concrete and steel. Neither we shall use the constitutive relationships which relate the complete stress strain curve of each material. Rather, we shall use only the ultimate strength of a member under shear, the strength of a material under shear, to get the ultimate shear strength capacity of a member. The strength of concrete under shear, although based on test results, is empirical in nature. The equation that we shall use for the shear strength of concrete is not related with any stress strain curve. That equation is just based on the strength the concrete has, and this is based on test results. Shear stresses generate in beams due to bending or twisting. The two types of shear stress are called flexural shear stress and torsional shear stress respectively. In this module, the analysis for shear refers to flexural shear stress. The torsional shear stress will be covered under analysis for torsion. Thus, the shear that we shall consider at this beginning is the shear due to flexure. The shear due to torsion will be covered in the later part of this module. To understand flexural shear stress, the behavior of a simply supported beam under uniformly distributed load without prestressing will be explained first. The presentation will be in the following sequence. First, we shall study the stresses in an uncracked beam. An uncracked beam is considered as a homogeneous beam where the effect of steel is negligible. Second, the types of cracks generated due to the combination of flexure and shear will be discussed. Next, we shall move on to components of shear resistance and the modes of failure due to shear. And finally, we shall see the effect of prestressing force in the shear resistance of the concrete member. First, the stresses in an uncracked beam. Here, we are seeing a simply supported beam subjected to uniformly distributed load. We are considering 2 points in the beam. One lies at the neutral axis and the other lies close to the tension phase. For such a beam, from basic structural analysis, we know that the shear force varies along the span, it varies linearly, and the moment also varies along the span and it varies along a parabolic curve. If we look at the stresses at any point of the beam, the variation of normal stress along the depth is linear. It is compressive at the top and tensile at the bottom. The variation of shear stress at a section along the depth is parabolic in nature, where the shear stress is 0 at the top and bottom and maximum at the neutral axis. Thus, the two types of stresses, the normal stress and the shear stress in a beam under flexure, have their maximum values at different locations. At a particular section, the flexural stresses are maximum at the top or at the bottom and minimum at the neutral axis, whereas the shear stress is maximum at the neutral axis and is minimum at the two edges. Under a general loading, the shear force and the moment vary along the length. The normal stress and the shear stress vary along the length as well as along the depth. What we had seen in the previous graph is that the shear force and the moment vary along the length. If I look at a particular section, the shear stress varies along the depth as well as the flexural stress. Thus, if we look the variation of the shear or the flexural stress point by point, it varies along the span as well as it varies along the depth. The combination of the normal and shear stresses generate a two-dimensional stress field at a point. In the analysis for shear, we are entering into a new concept, which is the two-dimensional stress field. That means there are normal stress in one direction and then there is shear stress, and this combination of normal and shear stresses generate a two-dimensional stress field. At any point in the beam, the state of two-dimensional stresses can be expressed in terms of the principal stresses. The principal stresses are the stresses in the planes where there is no shear stress. The Mohr circle of stress is helpful to understand the state of stress. These concepts were covered in our basic structural analysis. We shall review this again in the light of analysis for shear. Before cracking, the stress carried by steel is negligible. Hence, we can neglect the presence of steel in the concrete beam. When the principal tensile stress exceeds the cracking stress, the concrete cracks and there is redistribution of stresses between concrete and steel. It is easier to understand the state of stress before the cracking of the member, which we can derive by analyzing the beam by elastic analysis. After the cracking of the member, the state of stress is more complicated because there is redistribution of stresses between concrete and steel, and with increasing load the concrete enters into its nonlinear behavior, and the steel also after yielding enters into its nonlinear behavior. For a point in the neutral axis, which we are representing by the element 1, the shear stress is maximum and the normal stress is 0. That means, when we are considering this small element at the neutral axis, the shear stress V is maximum and the shear stress generates a two-dimensional stress field, whereas there is no normal stress at the neutral axis. From this state of stress, if we draw the principal stresses, the shear stress generates a biaxial tensile compressive stress field. Sigma 1 is the tensile stress and sigma 2 is the principal compressive stress. The principal tensile stress sigma 1 is inclined at 45 degree to the neutral axis. Thus, if we try to understand the state of stress by the help of a Mohr circle, what we see is for the vertical and the horizontal surfaces, the state of stress is the top and the bottom of the Mohr circle, where there is shear stress V, but there is no normal stress. But at a surface which is inclined at 45 degrees, we have the principal stresses. In one side there is the principal tensile stress, and in the perpendicular side we have the principal compressive stress. The magnitude of sigma 1 and sigma 2 are same under a pure shear. Since the shear force is maximum near the supports, cracks due to shear occur around the neutral axis near the supports and perpendicular to sigma 1. As I said that if we look point by point along a beam, first the shear force is maximum near the supports, and next the shear stress varies along the depth, and that is maximum at the neutral axis. Hence, the cracking due to shear we expect to occur first near the supports and around the neutral axis. These cracks will be normal to the principal tensile stress sigma 1. Thus, the understanding of the inclination of the principal tensile stress helps us to understand the inclination of the cracks due to shear. In this sketch, we find that under this pure shear, since sigma 1 is inclined at 45 degrees to the neutral axis, the cracking which occurs perpendicular to sigma 1 is also inclined at 45 degrees to the neutral axis, and this is the inclination of the cracks due to pure shear. For a point near the bottom edge, which is element number 2, the normal stress is maximum and the shear stress is close to 0. That means below the neutral axis, the normal stress is tensile, the shear stress is small. The principal stresses are as follows. Here, the inclination of sigma 1 is less than 45 degrees to the neutral axis. The value of sigma 1 is much larger than the magnitude of sigma 2, which is the principal compressive stress. If we plot the Mohs circle, we find that the state of stress in the horizontal and the vertical surfaces can be denoted by these 2 points. For the vertical surface, the state of stress is given as F, V. It has both the normal stress and the shear stress, whereas for the horizontal surface, it has only the shear stress and the point lies in the vertical axis. The principal tensile stress sigma 1 is almost parallel to the bottom edge. That means the more we go close to the bottom edge, sigma 1 becomes more and more parallel to the bottom edge. The value of alpha is much smaller than 45 degrees. Since the moment is maximum at midspan, cracks due to flexure occur near midspan and perpendicular to sigma 1. It starts from the bottom of the beam and gradually it goes up, and if we see the state of stress, that the inclination of the crack is perpendicular to sigma 1. Since sigma 1 is almost parallel to the bottom edge, the cracks will be starting as perpendicular to the bottom edge. In this figure, we see that the crack is almost perpendicular to the horizontal axis, and when we come to the bottom edge of the surface, this cracks becomes perpendicular to the bottom edge. With this understanding of the state of stress for an uncracked beam, we are now moving on to understand the types of crack that generates in a beam under flexure. The types and formation of cracks depend on the span to depth ratio of the beam and the loading. In the following figures, the formation of cracks for a beam with large span to depth ratio and uniformly distributed loading is shown. The formation of cracks in a reinforced concrete beam is inherently variant in nature. Wherever there is a weak point in the concrete beam, the crack propagates through that point. Instead of going into the detailed analysis of a crack formation, we are trying to have a visual representation of the growth of cracks, which will help us to understand the mechanism of crack formation and finally the failure of concrete due to shear. For a long beam, that means the span to the depth ratio is large. For such a beam under uniformly distributed load, the crack starts due to flexure and it starts from the bottom of the beam near the midspan. In this sketch, we find that the first cracks that are initiated are near the middle of the beam and it starts from the bottom. Since the moment is maximum near the middle and the flexural stresses is tensile and maximum at the bottom, the cracks generate from the bottom surface, and these cracks are called flexural cracks because they have generated due to the maximum value of the moment. As we go on increasing the load, we find those more number of flexural cracks, and those cracks have increased in size. But we also find the formation of some flexural shear cracks. That means cracks are generating due to flexure, but then they are propagating due to the effect of shear. Those are called flexure shear cracks. Such type of cracks are initially perpendicular to the bottom edge, but as they increase, they get inclined to the neutral axis. And we also observe some web shear cracks which occur due to the large value of shear near the supports. Near the supports, the moment is very small, and these cracks form at the neutral axis because the shear stress is maximum at the neutral axis. There is no flexural stress at the neutral axis, and moreover, the flexural stress near the supports is very small because the moment is very small. Hence, the cracks that are initiated by shear alone are near the supports, and they are inclined to the neutral axis at an angle of 45 degree. If we load the beam further, then we find a complete picture of the types of crack that is generated in the beams. In the middle region, we have the flexural cracks which are perpendicular to the axis of the beam, and they start from the bottom and propagate upwards. On the two sides of the flexural cracks, we have flexure shear cracks. They start at the bottom. Initially they are perpendicular, but then they gradually get inclined due to the effect of shear. This type of cracks are a transition between the web shear cracks and the flexural cracks. And near the supports of the beam, we find web shear cracks which generate near the neutral axis of the beam and are inclined to the neutral axis. And these are the three types of cracks that are generated in a long span beam under uniformly distributed load. The crack pattern can be predicted from the principal stress trajectories. In this figure, the solid lines give the trajectories of the compressive stress, and the dotted lines give the trajectories of the tensile stress. As we know that the cracks form perpendicular to the tensile stress, or they are parallel to the compressive stress. Hence, the formation of the cracks follows the stress trajectories of the compressive stress, and what we find that near the middle span the cracks are perpendicular, whereas when we go closer to the support, the cracks at the neutral axis are inclined. Thus, the crack pattern in a reinforced concrete beam can be explained by the help of the trajectories of the principal stresses of a homogeneous beam. For a simply supported beam under uniformly distributed load without prestressing, three types of cracks are identified. The flexural cracks, these cracks form at the bottom near the midspan and propagate upwards. Web shear cracks, these cracks form near the neutral axis close to the support and propagate inclined to the beam axis. Flexure shear cracks, these cracks form at the bottom due to flexure and propagate due to both flexure and shear. Next, we are moving on to understand the components of shear resistance in a reinforced concrete beam. This is studied based on the internal forces at a flexure shear crack. The components are as follows. Thus, we are seeing the free body of a section of a reinforced concrete beam. This section has been drawn as per the direction of a flexural shear crack. It is perpendicular to the bottom edge, but as we go up, this crack is getting inclined to the neutral axis. What we observe is that the shear stress is resisted by several components in the beam. The first component is the component of shear resistance due to the concrete under compression. Above the tip of the crack, the concrete is uncracked, and this part of the concrete can carry shear just like a material, homogeneous material. Next, since the crack traverses the stirrups carry shear after the cracking of concrete, and that is represented by Vs. The crack surface is not smooth, it is an irregular jagged surface, and there, due to the interlocking of the aggregates, we have a component called aggregate interlock, and that is denoted as Va. We have the dowel action. That means whenever a longitudinal bar is tried to be shifted along a direction perpendicular to the axis, then it generates some resistance which is called the dowel action. This action generates when the longitudinal bar is properly inserted within the concrete and the bond hasn't deteriorated. The dowel action also provides some resistance to shear. For a prestressed concrete beam, we have another component which is the vertical component of the prestressing force for an inclined tendon, and that is represented as Vp. Thus, the value of Vp depends on the inclination of the tendons. To summarize, the components of shear resistance are as follows. We had Vcz, which is the shear carried by uncracked concrete. Va is the shear resistance due to aggregate interlock. Vd is the shear resistance due to dowel action. Vs is the shear carried by stirrups. Vp is a vertical component of prestressing force in inclined tendons. The magnitude and the relative value of each component change with increasing load. Once we have identified these components, we have to understand their individual contribution in the shear resistance of the concrete. Their individual contribution varies as the load is increased. In the initial stage, after the cracking, the aggregate interlock and the dowel actions are high, but as the load is increased, as the cracks open up, the aggregate interlock gets reduced. As the bond between the steel and the concrete gets disrupted near the cracks, the dowel action gets reduced. The zone of concrete under compression gets reduced with the propagation of the cracks, thus Vcz gets reduced. Finally, it is the Vs which increases and resists the external shear. Next, we are studying the modes of failure due to shear. For beams with low span to depth ratio or inadequate shear reinforcement, the failure can be due to shear. A failure due to shear is sudden as compared to a failure due to flexure. Earlier, when we studied the behavior of a beam under flexure, we had studied the moment curvature curve and we had studied the ductility. We understood that after the steel yields, the section is able to resist the strength with some large deformation. That is called ductility in the moment versus curvature curve of a beam. But unlike the behavior in flexure, the failure of shear is quite sudden. It is a brittle failure as compared to the flexural failure. The cracks open up suddenly and the beams tend to fail in a brittle mode. 5 modes of failure due to shear are identified. The occurrence of a mode of failure depends on the span to depth ratio, loading, cross section of the beam, amount and anchorage of reinforcement. The modes of failure are explained next. The first one is the diagonal tension failure. In this mode, an inclined crack propagates rapidly due to inadequate shear reinforcement. That means if the shear reinforcement is not adequate enough, the cracks that have formed due to shear or flexure shear, they will propagate through the depth of the beam quickly, and we see that the right part of the beam has got literally separated from the left part, and this is an instance of a failure due to shear, and this type of failure is called the diagonal tension failure. The second one is a shear compression failure. There is crushing of the concrete near the compression flange above the tip of the inclined crack. If the concrete near the top flange is not strong enough, then as the inclined crack propagates, there will be crushing of the concrete at the top of this crack. This will be also affected by the amount of moment at that particular section, and when there is crushing of the concrete at the top of a flexural shear crack, that type of failure is called a shear compression failure. The third type of failure is the shear tension failure. Due to inadequate anchorage of the longitudinal bars, the diagonal cracks propagate horizontally along the bars. If the longitudinal bar is not properly anchored at the support, then the diagonal cracks, once it hits the level of the longitudinal bars, the crack propagates horizontally towards the supports, and the bond between the concrete and steel gets disrupted. It leads to an anchorage failure, and this type of failure is called the shear tension failure. Thus, the shear tension failure leads to a separation of the longitudinal bars with the concrete, and which leads to an anchorage failure of the longitudinal bars. The fourth type of failure is the web crushing failure. The concrete in the web crushes due to inadequate web thickness. Thus, this type of failure happens in an eye girder if the width of the web is small, that since there is a principal compression in an inclined direction, if the web is not strong enough, then it will crush due to that principal compression. The fifth type of failure, the arch rib failure, is observed in deep beams where the span to depth ratio is small. The web may buckle and subsequently crush. There can be anchorage failure or failure of the bearing. This type of arch rib failure is characteristic of a deep beam where the span to depth ratio is small. There can be crushing of the concrete in the web, there can be anchorage failure and also crushing of the concrete near the bearing, and this type of failure due to the arch action within the dip beam is called an arch rib failure. The objective of design for shear is to avoid shear failure. The beam should fail in flexure at its ultimate flexural strength. Hence, each mode of failure is addressed in the design for shear. The design involves not only the design of the stirrups, but also limiting the average shear stress in concrete, providing adequate thickness of the web, and adequate development length of the longitudinal bars. Once we have understood the modes of failure, we can understand the objectives of the shear design. The shear design includes not only the design of stirrups, but it includes other detailing requirements which checks the different modes of shear failure. We have to have adequate thickness of the web, we have to have adequate anchorage of the longitudinal bars, and we have to have the stress in the concrete limited, because if the concrete crushes, then it will lead to a sudden shear failure. As the shear failure is brittle, we do not allow shear failure before the concrete reaches its final strength. The objective of the design is that a beam should fail in flexure at its ultimate strength, and it should not fail in shear before it reaches its ultimate strength. Next, we are studying about the effect of prestressing force. In presence of prestressing force, the flexural cracking occurs at a higher load. For type 1 and type 2 sections, there is no flexural crack under service loads. This is evident from the typical moment versus curvature curve for a prestressed section. We had seen these curves earlier, that for a reinforced concrete beam, the moment versus curvature curve passes through the origin. After cracking, there is redistribution of stresses, there is increase in curvature, and then we observe nonlinearity in the behavior due to the nonlinearity of concrete. Once the steel yields, then we observe the nonlinearity of the steel as well, and gradually the curve tapers off to the ultimate strength. If we have prestressing in the beam, the curve gets shifted from the origin, which means that for zero curvature, we need to have an external moment. In other words, in absence of any moment, there is a negative curvature, which is the cambering effect due to prestressing. As we increase the load, the linear behavior is up to a much higher level. Usually, the prestressed concrete members are designed such that it does not crack under service loads. This type of sections has a cracking load which is higher than the service load. After cracking, we observe the nonlinearity in the behavior and the strength tapers off to the ultimate strength. These two curves have been drawn for a reinforced concrete and a prestressed concrete section, which have equivalent flexural strength. In presence of prestressing force, the web shear cracks also generate under higher load. Thus, what we observe is whenever there is a prestressing force, the flexural cracks, the web shear cracks, both of them occur at a higher load. With increase in the load beyond the cracking load, the cracks generate in a similar sequence. That means for a long beam, we will observe flexural cracks to occur first, then we shall observe the flexural cracks to change to a flexure shear cracks, and then we may observe web shear cracks near the supports. The sequence is similar, but the inclination of the flexure shear and the web shear cracks are reduced depending on the amount of pre-stressing and the profile of the tendon. Let us understand the effect of pre-stressing force for a beam with a concentric pre-stressing force PE. This is a simply supported beam with a uniformly distributed load subjected to a concentric pre-stressing force PE. We shall observe the state of stress for an element which is at the neutral axis. For a point at the neutral axis, which is represented by element 1, there is normal stress due to the pre-stressing force, which is compressive and denoted as minus FPE. This is the main difference with a reinforced concrete, that in a reinforced concrete at the neutral axis we did not have any normal stress, it was a case of pure shear stress. But for a pre-stressed concrete beam, we are not only having a shear stress at the neutral axis, but we are also having a compressive stress due to the pre-stressing force. Due to this, the state of stress is such that the principal tensile stress sigma 1 is inclined to the neutral axis at an angle greater than 45 degree. The principal tensile stress sigma 1 is much smaller compared to the principal compressive stress sigma 2. If we plot the Mohr circle for this state of stress, then this point corresponds to the vertical surface which has the shear stress and the normal stress, which is negative minus FPE. The point lying in the vertical axis is the horizontal surface which has only the shear stress, and we find that the magnitude of sigma 1, the principal tensile stress, is much smaller than the magnitude of sigma 2, which is the principal compressive stress. Since the sigma 1 is inclined at an angle greater than 45 degrees, the crack which occurs perpendicular to sigma 1 or parallel to sigma 2 is inclined at an angle which is lower than 45 degrees in presence of the pre-stressing force. Thus, for a pre-stressed concrete beam, the formation of the cracks can be explained by the help of the state of stress. What we had seen was for a concentric pre-stressing force. If the pre-stressing force is eccentric and if the profile of the tendon is parabolic, then the analysis gets more involved, but the basic concept remains same, that due to the effect of pre-stressing force, the inclination of the cracks due to shear gets reduced and the principal tensile stress is much smaller than the principal compressive stress. Hence, the cracking occurs at a much higher level as compared to a reinforced concrete beam. The crack pattern that occurs in a pre-stressed concrete beam is shown in this figure. Here you can see that the flexural cracks is much smaller as compared to a reinforced concrete beam. The number of cracks is small. The flexural shear cracks is more inclined, and the web shear cracks is also small. They are more inclined to the neutral axis as compared to the cracks in a reinforced concrete beam. If we compare the cracking pattern in the two types of beam, what we observe is that in a reinforced concrete beam, the flexural cracks is much more compared to a pre-stressed concrete beam. The growth of the flexural cracks is more than in a pre-stressed concrete beam for the same load. The flexural shear cracks are more inclined in a pre-stressed concrete beam. The growth of the flexural shear cracks is less in a pre-stressed concrete beam. the web shear cracks is at an angle of 45 degree in the reinforced concrete beams, whereas for a prestressed concrete beams, the web shear cracks, the inclination is smaller, and the amount of cracking throughout the beam in a prestressed concrete beam is much lower as compared to a reinforced concrete beam. This is the big benefit of the prestressing, that the cracking in the beam is much less as compared to a reinforced concrete beam. After cracking, in presence of prestressing force, the length and crack width of a diagonal crack are low. Thus, the aggregate interlock and zone of concrete under compression are larger as compared to a non-prestressed beam under the same load. Hence, the shear strength of concrete, which is represented as Vc, increases in presence of prestressing force. This is accounted for in the expression of Vc. The main advantage of prestressing is being reflected in this observation, that since the growth of cracks in a prestressed concrete beam is small, we have higher aggregate interlock in a prestressed concrete beam, we have a larger concrete in compression for a prestressed concrete beam. Both these effects increase the capacity of the concrete to resist shear. Thus, in a prestressed concrete beam, the capacity of concrete to resist shear, which is denoted as Vc, is higher as compared to a reinforced concrete beam. In addition, we also have the vertical component of the prestressing force if the tendon is inclined. Thus, as a summation, the shear capacity of a prestressed concrete beam is larger than a reinforced concrete beam, and this helps us to check the different modes of failure under shear, provided we do the other detailings properly, and the beams are expected to reach their ultimate flexural capacity before it fails under shear. In today's lecture, we studied the analysis for shear, and we learned the important concept of shear. First, we studied the stress condition in an uncracked beam. We understood this concept from the basic structural analysis. For a simply supported beam under uniformly distributed loads, the shear force varies along the length of the member. The moment also varies along the length of the member. The shear force is maximum near the supports and minimum at the midspan, whereas the moment is minimum near the supports and maximum at the midspan. If we look at the variation of the stress along the depth, the flexural stresses which generate normal stresses, they are maximum at the top and at the bottom and minimum at the neutral axis, whereas the shear stresses is minimum at the top and the bottom and maximum at the neutral axis. If we see the variation of the normal and shear stress in a beam along the length and along the depth, we are able to understand the formation of the cracks. What we observe is that at around the midspan, since the flexure is high, the normal stresses at the bottom of the beam leads to cracks, which starts from the bottom of the beam and grows up. Those are called the flexural cracks. If we come near the supports, the normal stresses are small since the moment is small, and the shear stress is high near the neutral axis, and also the shear force is high near the supports. Hence, the cracking due to shear occurs near the neutral axis. We understood the inclination of the cracks from the state of stresses. For a point near the support at the neutral axis, it is under pure shear stress, and a pure shear stress is equivalent to a biaxial stress field where the tensile and compressive principal stresses are equal in magnitude. The crack occurs perpendicular to the principal tensile stresses, and they are inclined at an angle of 45 degree to the neutral axis. Thus, the web shear cracks occur at an angle of 45 degree. In between the web shear cracks and the flexural cracks, we have a transition region where we observe flexure shear cracks. These cracks generate due to the flexural stresses from the bottom of the beam, but they propagate and get inclined to the neutral axis due to the effect of shear, and hence these are called flexure shear cracks. The crack pattern can be explained from the principal stress trajectories of a homogeneous beam. After the concrete cracks, there is redistribution of stresses, and we understood the components of shear resistance from the free body diagram of a concrete beam adjacent to a flexural shear crack. Among the components of shear resistance, the first we have the component for the uncracked portion of the concrete above the tip of the crack. Next, we have the aggregate interlock effect, which occurs because the cracks are not smooth. Then we have the contribution of the stirrups, which is represented as Vs. We also have observed that the longitudinal bars provide some resistance due to the dowel action. This component of the shear is represented as Vd. For a prestressed concrete beam, we have a vertical component of the prestressing force in an inclined tendon, and that is represented as Vp. Now, the relative contributions of these various components in the shear resistance varies as the load is increased. For smaller loads after the cracking, the aggregate interlock, the contribution of the concrete under compression and the dowel actions is high. As the load is increased, as the cracks propagate and the cracks open up, the aggregate interlock reduces, the zone of concrete under compression reduces, the bond between the concrete and the steel gets deteriorated, and hence the dowel action gets reduced. The shear stress carried by the stirrups gets increased till the yielding of the stirrups, and hence what we find that at ultimate strength, the summation of the dowel action, the aggregate interlock and the concrete under compression drops down to a minimum value, and the contribution of the stirrups attains a maximum value and stays constant at the value where the stirrup starts to yield. This is the basis of developing the equations for shear resistance. Now, from the components of shear resistance, we moved on to the modes of failure due to shear. First, we had seen the diagonal tension failure, that if there is inadequate stirrups, then the diagonal cracks propagate through the depth of the beam quite rapidly, and this will lead to a sudden failure of the beam. The second we found was a shear compression failure, that at the tip of a diagonal shear crack, the concrete under compression can crush. This will be also affected due to the flexural compression, and we need to have adequate concrete at the top to resist this shear compression. We found another type of failure, which is a shear tension failure, that if the longitudinal bars are not properly anchored near the support, then the diagonal cracks, after it reaches the level of the steel, propagates horizontally, disturbs the bond between the steel and the concrete, and the steel bar tries to pull out from the ends, which leads to an anchorage failure, and this type of failure is referred to as the shear tension failure. The fourth type of failure we have seen was the web crushing failure. This occurs for beams with thin webs like an eye girder, where due to the principal compressive stress, the concrete in the web may crush. The fifth type of failure is observed for deep beams where the span to depth ratio is small. In a deep beam, there is an arch action, and due to the arch action, we may find a failure which is termed as the arch rip failure, which consists of the crushing of the concrete in the web, crushing of the concrete near the bearing. It can also have an anchorage failure. This type of failure, of course, is not observed for long span beams. Now, next we moved on to the effects of prestressing force. What we found is that when there is a prestressing force, there is an additional normal stress at the level of the neutral axis, which is compressive. It influences the principal stresses and their inclination. The principal tensile stress is much smaller in magnitude than the principal compressive stress. The inclination of the cracking is lower than 45 degrees. Cracks is much less in a prestressed concrete beam as compared to a reinforced concrete beam, and the cracks are also inclined in small angle compared to the reinforced concrete beam. This has a direct benefit in the shear resistance of the section. The aggregate interlock is sustained. The zone of concrete under compression is higher, and the dowel action is also sustained. Thus, the shear capacity of a concrete beam increases in presence of prestressing force. The objective of shear design is to check the modes of shear failure such that the beam attains its flexural capacity before it fails in shear. It involves not only the design of stirrups, but also other detailing to check the different modes of failure. In our next class, we shall move on to the formulation of the shear resistance from which we are able to design for the shear in a prestressed concrete beam. Thank you.